So far, all we've really used calculus for is to talk about, finding the equations of tangents and things like that. But the derivative is far more powerful than that. Our derivative measures a rate of change. So anytime you've got a quantity changing with respect to something else, we can use calculus for, if we can come up with some function for that quantity. Most of the time, it's going to be time, as things change with respect to time. And there's so many things that we want to measure that changes as time goes on. So what can we tell from our derivative? Some simple stuff to start off with. Well, the steeper the curve, the faster that quantity is changing. So here's a curve at point P. So that's some graph of some quantity changing, some y changing with respect to x. As I say, it might be something with respect to time, it could be whatever. But at the point P, what I can tell from that graph is I know the derivative is greater than 0, so therefore whatever that quantity is, whatever that function is, it must be increasing, getting bigger. If I'm at one of the vertices there, so Q, now I know that's when the derivative is equal to 0. So that means that function is stationary there. It's not changing at that point. And then of course it could be now going down. So there we are at R, and the derivative is negative. So I now know that rate of change is decreasing, getting smaller. But so the beauty of this is I don't actually need the graph. All I need is the derivative. And from that I can tell what the graph's doing. So it can save us a bit of time. Some other things. If I've got 2 points on the graph, the slope of that secant, so secant being a line that just cuts a curve in 2 or more places. So if I found the slope of that secant, that gives me the average rate of change. What's more useful is the slope of the tangent, which gives me an instantaneous rate of change. That's far more interesting. Let's think about it, you're driving in a car. Policeman pulls you over because you've been speeding, because he's measured your instantaneous rate of change, got the radar gun out and going too fast. You can't sit there and say, oh, no, officer, if you look at my average speed over the last 10 minutes, actually I'm fine, I've been below the speed limit. They won't cop that, that's just, no. They're interested in the instantaneous rate of change. Let's have a look at this example. We've got a water tank, and water is being emptied out of our tank. So Q is representing the number of litres of water that's in the tank, and we've got a function that's going to measure that. There it is, Q equals 1,000, 2 minus T squared. First question, well, what's the rate the tank is being emptied at any time? So in other words, come up with a formula that'll describe the rate at which it's being emptied. Well, that's our derivative. How is Q changing with respect to time? So what is the Q to T? So I just have to differentiate this function. And with a bit of anarchy, bring down the power, lower the power, diff inside, we can see there's our formula. Now, it's an actual physical thing, so I'll put some units on it. It must be, given what they've told me with the dimensions, it must be in litres per minute, this particular one. Okay, well, how long does it take for the tank to empty? I've now got 2 formulas I can use. I've got a formula that tells me the actual quantity, but I've also got a formula that tells me the rate of change. In this case, it's the first one I'm interested in, because I want to know when is Q equals 0, when is it emptied out. So solving that, we get T equals 20. So I know, right, after 20 minutes the tank's going to be empty. At what time is it flowing out at a rate of 20,000 litres per minute? Why would I want to know something like that? Maybe it's got something to do with the valve in the tank, and it can only handle an output of a certain amount. So it wants to know when it gets to this rate, I need to do something to fix it. So when is it flowing out at 20,000 litres per minute? Well, now it's the derivative I'm going to use. I want to know when is the Q to T. It would be negative because it's flowing out, it's decreasing. So it's going to be negative 20,000. And we solve that little equation, and we know after 10 minutes. So after 10 minutes we want to be having a look at this and see what's happening. What's the average rate at which the water flows out? So if for some reason they're interested in the average rate, then I need 2 points. Now, they've said the first 5 minutes. So I need to know what's happening at T equals 0 and there's 400,000 litres in there. And at t equals 5, it's now reduced down to 225,000. So the average would end up being, and that was just like a slope formula really, one minus the other, and we end up with negative 35,000, and so that would be our average rate. One of the key things calculus has been used for over the years is motion. That's probably why it was originally come up with. It was actually about motion of the planets they were interested in, is where it all came from. It actually was discovered, right? Calculus was not invented, it was discovered. Because it's always been there. It's not like someone just all of a sudden invented it and there it was. It's always been there, it just had to be discovered. There's a German fella, Gottfried Leibniz, or is it Leibniz? Not sure how you say his surname. So in 1674, he was aged 28 at the time. Now, it's his notations actually, even though the other bloke gets a lot of the credit, it's his notations that we tend to use in calculus. The other bloke has done a lot of things, you've probably heard of him, Isaac Newton. 1665 is when he came up with the idea. He was 22 at the time. 22. Newton used calculus to explain these laws of motions. You've probably heard of Newton's first law of motion, second law of motion, and that. And this is why he came up with this idea of how he could mathematically explain these laws of motion. Now, the dot notation that Newton came up with, we tend to use for motion still. So let's talk about these three things that are very important in motion: displacement, velocity, and acceleration. Displacement. Now, in maths, we tend to use the pronumeral x a lot for displacement. I think in physics you use s. It doesn't really matter, it's just a pronumeral at the end of the day. But what is displacement? Well, it's distance from a point, but with direction. So plus or minus now actually means something. It tells you the direction in which you're travelling. So we sort of always assume we're travelling in a straight line, and that line may as well be the number line. And so if I have a positive displacement, I think of myself on the right-hand side of 0. And if I have a negative displacement, I think of myself on the left-hand side of 0. Velocity, well, V obviously is used for velocity. Newton's notation would have been x with a dot on top. So x dot would have been velocity. But of course we know it's a rate of change as well. So we could use dx to t. How does displacement change with respect to time? So it's the rate of change of displacement with respect to time. So it's the same as speed, but with direction. So again, the plus or minus tells you which direction am I travelling in. I get a negative velocity, then I'm travelling, well, again, if we think of our number line, we're travelling to the left. If I've got a positive velocity, I'm travelling to the right. And then we have acceleration. Now there's all sorts of notations we could now use. A, obviously, for acceleration, but using Newton's dot notation, it could be v with a dot because it's the first derivative of velocity. It could be x with two dots, because if you differentiate it twice, you would get to acceleration. You could use dv to t, because acceleration is the rate of change of velocity with respect to time. Or it could be what we call, and we haven't really looked at this bit yet, but the second derivative of displacement with respect to time. And we'll probably talk more about that later, but we'll talk about the second derivative. Up the top there, I've drawn a displacement time graph now. So you'll notice x is actually on the vertical axis this time, and t is on the horizontal. Underneath it, a velocity time and an acceleration time. Now, I suppose my question is if that curve represents a displacement time equation, how can I draw the velocity time equation and the acceleration time equation? So I look at some key features. When my displacement graph is stationary, that's what we said at the vertex, the tangent would be horizontal. So there's one of them. So when that is stationary, well, stationary means velocity is 0. It's stationary, it's not moving. So therefore, on my velocity time graph underneath that, I can plot a t-intercept. And there's another one there, so that would also be a t-intercept. Okay, what else did we find out? When the displacement graph is increasing, so that section there, the curve's going up, but all the way there, the derivative is positive. Because if I was to draw a tangent at any point there, I'd end up with a positive slope. So therefore, on my velocity time graph, I don't know exactly where, but I know I must be in the positive area. So I must be above the t-axis. And it's also increasing for that section on the right, so I know it's going to be positive on that section on the right as well. Well, similarly, when my displacement graph is negative, it's decreasing. So velocity will end up being negative. So I know I'm down below in that section there. There's another key feature to look for. The velocity graph is stationary. When will that happen? It's going to happen there. How do I know that? I go back to the displacement graph and I look for what's called a point of inflection. See how that curve's changing from being a concave down shape to a concave up shape? That point where it changes is what we call an inflection point. The curve inflects. So at that point, on the next graph down below, the velocity one, that's where I'm going to have a stationary point. Now I could do the same with the velocity and acceleration graphs now to create the acceleration. So that stationary point would become a t-intercept on the acceleration. It's decreasing on the left-hand side, so it's negative in acceleration. And on the right-hand side, it's increasing. I'd end up with a straight line. Now, if you think about the calculus, it kind of makes sense. That first graph looks like a cubic. Differentiate a cubic, you get a quadratic or a parabola. Differentiate a quadratic, you get a linear function. So acceleration ends up being a straight line. So these are all ideas that Newton came up with his using calculus for motion. And we'll look much more into this later. Like this is just a brief touch on it to see where calculus can take us and what we can use it for. So let's have a play with some of those. 9J.